Hey everyone, so I just want to finish up all the inclined plane problems in the rest of this topic. So we'll start off right off the bat, work on this one, pause the video, work itself, and we'll go over in a second. All right, now one thing to keep in mind is you want to pay attention to the diagram that they give you, but keep in mind that the forces they give you are not all of them. They pretty much give like external forces or extra forces. There are two other ones that we have to keep in mind, namely the force of gravity and the normal force. A lot of times when they give you FBDs for problems, they won't give you those forces. So you need to make sure that you include them. So here they have the applied force going up and the friction force going down. We want to add in our other forces. So we have our normal force going up at an angle like this. And then keep in mind that instead of drawing the force of gravity onto the inclined plane, we include the perpendicular component and the parallel component. All right. Now that we have it all like this, everything becomes easy peasy. We can figure out what these forces are. In particular, the parallel force is the only one that I care about because in order to find the force going up the incline, it's moving at a constant speed. That tells me all of these forces are balanced. So this force pulling up must be equal to these two forces going down. F parallel can be replaced with FG sine theta. Uh, Plugging all the numbers in, keeping in mind that this is already in Newton, so I don't have to convert it again. I end up getting that the force pulling it up is going to be 8 newtons altogether. All right. Here's the next one. Pause the video, work itself, and we'll go over in a second. All right. So this question wants us to figure out the minimum coefficient of friction needed to keep at rest. Again, we're going to start off with our go-to draw an FBD. So we have the, I guess I didn't put it in here, we have the perpendicular component, the parallel component, the normal force, and the force of friction. Because the object is all at rest, we know all of these forces are going to be equal to 0. So the force of friction is going to be equal to the parallel force, which I write up here. So F friction can be replaced with Fg sine theta. I also know that the normal force is going to be equal to the perpendicular component, again, because those two are balanced out. So the normal force is going to be Fg cosine theta. And when I use the equation for friction, because we're looking for the coefficient of friction, meaning that we have to use this equation Ff equals mu Fn, I plug in the numbers and I get that the coefficient of friction at minimum has to be equal to 1. Right? Now, one interesting thing is that up until the very end, I did not plug in any numbers to show you this nice little interaction that the coefficient of friction, putting something on an inclined plane, actually depends purely is going to be equal to the max of the angle, or I guess I should phrase it the other way. The maximum angle that you can apply, that you can like raise an incline for before an object slips, will end up being equal to the coefficient of friction, meaning that it doesn't matter how much weight Santa Claus is in here. You know, we can double, triple, quadruple the weight, and this it would still slide at 45 degrees as long as the coefficient of friction was equal to 1. Right? So it's just an interesting thing because sometimes they do ask that of where they go the other way and they say that they give you two materials and they'll ask you what is the maximum angle that you can lift up the incline to before it begins to slip. And the idea is just to realize that the mu would be equal to tan theta in that case, and then you just solve it for theta and you get your answer. All right, here's the next one. Pause the video, work itself. I'll go over in a second. All right. So another inclined plane, they give us all this information. They say that the person's going at some speed of 30 meters per second, but he comes to a stop. So this is an example where they're giving us information through kinematics to find the acceleration, and we're going to use that in order to kind of determine what the net force is. So it goes back to what I said before about how you want to keep in mind the web of connections between different topics and recognize what term, what variable connects each of the topics. And in the case of kinematics and forces, that one variable is acceleration. So I'm going to use this information, the initial velocity, the final velocity, and the distance to find the acceleration to get that the car was decelerating at 22.5 meters per second squared. In order to find the frictional force that the brakes are applying, I'm going to set the sum of the forces in the parallel direction equal to ma. The f of f, we're solving for it. So we move the parallel force over to the other side and replace that with fg sine theta. we use the acceleration that we just found and all this information that we have to find that the frictional force would have to be 3,300 newtons. All right, here's the next one. Pause video work itself. I'm going to go over in a second. All right, so here we have a block on an inclined plane. Now, one thing that you're going to see with with this question and future ones is these are examples where they incorporate the inclined plane force problems with kinematics. So we see a little bit of that. Now, I will actually point out that in a future unit, we're going to learn something. We're going to learn about what's called energy that will allow us to do this problem significantly easier. So I want you to keep this in mind that in order for me to do this through kinematics and forces, it's going to require probably 3 steps or so. But later on, when we learn about energy, you'll see that we can do it all in a single step. All right. So starting here, again, they want us to figure out the speed it's reaching the bottom. So that means we're going to have to use kinematics because none of our force equations use speed. So before I can find the use the kinematics to find the speed, I need to find the acceleration, and I'm going to have to use that using forces. So I do my whole net force equations. Again, there's a normal force, perpendicular force, parallel force. The parallel force, because it's frictionless, is the only force pulling it down the ramp. So it's going to be the parallel force equal to ma. Solve this, and we end up getting that the acceleration is going to be 10 sine 30, or 5 meters per second squared. So that's what the acceleration of the block is going to be down the incline. Using that acceleration with the kinematics, uh, I'm going to be able to do that. So based off of this, we have the initial velocity being equal to 0. We know the acceleration, and we're looking for the final velocity. The only equation that seems to make sense is the timeless equation because we don't have the time. The problem is that we don't have the distance it travels down the ramp, but what we could do is use SOHCAHTOA and trigonometry to figure out what the other sides of this right triangle are. So we know what the height of the right triangle is. So we could just do sine 30, divide that over to the other side, and we get that this is going to be 40. Um, just keep in mind this means the hypotenuse, not height. It's a little confusing with the term, but now that I have the distance that the block slides down, I can actually use the timeless equation, plug my numbers in, and I get the answer 20 meters per second square, 20 meters per second. Right. So again, with my experience, I'm able to quickly figure out what things I'm going to need before I can start doing it. However, you will find that this is something that you're going to end up doing too, though you might have to work backwards, right? We know that we're looking for final speed, and there's really only 2 questions that deal with that: the acceleration equation and the timeless equation. They don't mention anything about time, and while they don't tell me the distance it covers, they do give me this. So I actually could kind of recognize that I have some form of a distance provided. So maybe I'm going to use timeless, and then again, we'd work backwards and realize, okay, I have to find acceleration. Obviously, I don't have enough information to use kinematics for the acceleration, so let's focus on the forces since it's an inclined plane. What can we do with forces to find acceleration? So that's kind of the idea whenever I say working backwards, right? You get an idea of what equation you might work with, figure out what things you're missing, and just keep working backwards and think, well, how can I find this with the other pieces of information? All right, here's the next one. Pause video, work itself. We're going to go over in a second. All right, so they want the acceleration of the block. So they give us this information. Now, it may seem like we would want to do kinematics again because they're giving us distance and they're looking for acceleration. But the problem is they don't give us anything else. They don't give us time. They don't give us any velocities except for, I guess, the initial velocity. So we can't do that. So what we're going to end up doing is we're going to have to use forces. However, here's the problem. If I try to do some of the forces, equal to ma. The net force will be the parallel because again it's frictionless. I'm going to set this equal to fg sine theta, but the problem is I don't know what theta is. Well, what I can do is this is a right triangle, as they so nicely put it. What I can do is use these 2 distances to figure out what this angle is. Actually, interestingly enough, I don't even need to find the angle because I can actually combine this equation with SOHCAHTOA because sine of this angle is going to be equal to opposite over hypotenuse. So it actually turns out that I could just plug in 3/5 in for sine theta and basically bypass that whole entire step of finding what the angle is to find that the acceleration is 6 meters per second squared. Of course, you are allowed to do whatever you want. If you want to spend a little extra time to find the acceleration, by all means. Different people see problems differently. I just want to show you that this actually happens a lot where they'll give you kind of the information so that you can come up with essentially replacements or the SOHCAHTOA replace the SOHCAHTOA terms with their adjacent over hypotenuse expression so that you don't have to calculate for the angle. So sometimes they do it as a really nice thing, and it's good to kind of look out for it. Right, here's the next one. Pause the video work itself. I'm going to go in a second. All right. So here it is. The peak inclined plane problem. Here we have an inclined plane mixed in with a multi-mass system. Uh, like I said, for the most part, nothing really changes. We just have to combine our methods of dealing with inclined planes with our methods of dealing with multi-mass systems. For example, our very first step is always to draw an FBD, but specifically because it's an inclined plane, we have to make sure that we include the forces. Yeah, I want to actually draw these forces. So this one ends up having a perpendicular component here, oh, a normal force going this way. It's going to have a tension force going this way, a parallel component going this way. I apologize for how messy this is. This one's going to have a tension force going this way and a force of gravity going this way. And it says that this big mass is going to accelerate downwards, which means this object is going to accelerate upwards. So when I do my sum of the forces, I'm looking in the plane of, so that's the inclined plane step. The inclined plane step was to draw the FBD, but breaking up FG into its components. Once we break up the FG into its components, it doesn't, we don't even need to worry about it being an inclined plane anymore. In fact, what I can do now, if I really wanted to, was just turn this into a standard modified Atwood machine. You know, don't worry about this being on an incline, just flatten it out, keeping these forces in their directions, perpendicular to the surface and parallel to the surface. And we'd end up with a modified Atwood machine with the exact same answers. So that's what we're going to do here. So we have the FG of this block going down, positive. This FT is negative. This FT is positive. This F parallel is going to be down in the opposite direction, making it negative. So these tensions cancel out, and we end up getting FG of the big mass minus the parallel component of the little mass equal to the sum of the masses times A. So combining in our equations, kind of simplifying it, we end up getting this, because we're solving for a little m, so we have to be careful. We have to distribute this m over to both sides, get all the big m's to one side, all the little m's to the other side, and then solve for little m. Now we can actually plug our numbers in. Now, of course, you're free to have plugged in your numbers before. Like I've said this before, but personally, I do like to try to solve it in algebraic terms because it's something that we want to get used to, right? I've said before that the AP likes to have questions where you have to derive stuff and solve things algebraically, where your final answer will be in terms of variables rather than numbers. So you might as well get into the habit now and start answering as many of your questions as you can without plugging in numbers until the very end. Of course, you don't have to do that. You can plug in numbers right from the get-go, but it's good practice to at least try. Some questions don't really make it easy for you to do that. There are some questions where, uh, like this, where it just gets so messy and gross without plugging numbers in that it might look nicer to just, it might make more sense conceptually for you and might be able to follow it better if you just simplified, plugged in numbers right off the bat. But, you know, it's whatever. Plus, one other good thing about plugging in numbers, I guess, in the beginning, if you're really struggling with these problems, is that it removes this from being a physics problem and turns it into a math problem. I've said this before as well, that a lot of students tend to have an easier time dealing with math problems rather than a physics problem that becomes a math problem. I can give you a math problem without, with just X's and Y's, and people will be able to solve it. And then I could give you an identical physics problem where there's now some variable terms that you have to plug numbers into it, and all of a sudden it becomes a much more complicated equation simply because it has that looming air of physics over it. So sometimes that could help just plug in the numbers without the units, just so that you can get a handle of what's going on, and then turn it into a math problem. Replace the unknown with an X, stuff like that. All right. So one thing I wanted to show you, kind of as a joke, is that one thing I could do is I could actually combine a lot of the stuff that we're talking about. I can combine friction with inclined planes, with multi-mass systems, with all these other things that you could see. And these are all different variations of that. Now, I do want to point out that first off, you would never see these problems. Or I shouldn't say you would never see these problems, but some of these problems are less likely to be seen than others. Something like this probably wouldn't do it. I think these two might be also a little bit rare, but this one, this one, and this one really aren't that bad. They look very intimidating, but the idea is that if you approach it with the exact same methods and steps that we've been doing for both inclined planes and multi-mass systems and just forces in general, the problems break down significantly easier. The hardest part with these problems really is determining and coming up with that FBD. Because once you come up with the FBD and you can keep track of every single correct force, then it boils down very simply with the whole sum of the forces. It kind of, becomes a lot easier. The FBD is actually really the toughest part. In some problems, it can be very basic, but the only reason why this problem is actually as difficult as it is, or this problem, is because the FBD is a little bit complicated of what forces do I have, where are they going, and which ones are, Newton's third, and all that stuff. So I just want to point that out there that while a lot of these situations are not likely,